All right, so now let's look at this in terms of something being in parallel. And in parallel, what I'm focusing on, I guess I should show you, is this circuit right here. What does in parallel mean? Well, let's see. That means my current comes here. It has a choice. It can go straight ahead. It can go up and fill that capacitor, or it can come down and fill that capacitor. So in parallel means we have path options. There's not just one way I can go. So what is going to be different? Well, that one's easier to figure out, because if these are all different size capacitors, then that means if I fill the smallest, then current is going to go to, or the charge is going to go to the next line and just fill it, and then it'll go to the next capacitor and fill it. So what is different on these is the charge. What's going to be the same is going to be the potential difference between these two spots. So my voltage drop is going to be the same across all. In other words, you can think about it as we're going to figure out what our equivalent charge is, our equivalent capacitance. And that means that once I get through like this little block of circuitry, that if I'm starting off here at 10 volts, well, I had better go from this spot to this spot and lose all 10 to have conservation of energy stand. So my potential drop will be the same. Now the way we write these is to say our equivalent capacitance is going to be then just the sum of my capacitors. And that should kind of make sense, because this says this is how much charge I can hold for my circuit that I've created. And if that's the case, then it's just going to be the sum. I'm going to have different lines with different amount of charge if they're different capacitors, right? So let's take a look at this. I have current coming in, or charge coming in, and it can go this away or it can go this away. So this section here is in parallel. These two, C1 and C2, that's a straight line. So my Q is going to go through there. So this is in series. And then this whole gosh darn thing, this whole thing here, is in series with this fourth capacitor. So this is where I was alluding to for our capacitors when we first started talking about this, is that it's going to be really important to be methodical with how you're doing things. So if I want to figure out the charge and potential drop across each, then I can keep things straight. And what I always tell people to do is to start off with the actual circuit that you have. And just kind of like what I've been doing before when I was labeling charges, we're going to label our capacitors. So this is going out back to the battery, so AB. And let's see, let's be consistent with the drawing. So I'll call this 1, this 2, this 3, and this 4. So I always go after the low-lying flute, I suppose, or fruit in other parts of the world. And that's going to be to combine these two. Actually, I don't want that in the same color. Because what I'm going to need to do is combine things consistently, right? So these two things are in line. They're in series. I need to combine those so I can add this equivalent capacitor with this capacitor in parallel. So let me write out what that looks like. So then I'm going to have, my next step is going to have something like this. I'm going to have two capacitors in parallel. Let me label these. This is going to be, let's call this C, C, C. So this will be C12. However you want to do it. You don't have to use my notation. Here's C3. Oops, and I forgot to include poor C4 got left out. And here's C4. So my next step is I have these two in parallel. I want to combine them so I have two capacitors on a line. So I'm going to do this. This is going to be C123. So it's the equivalent capacitance of all three of these capacitors. And then C4. And then finally the last thing I will have is my equivalent capacitor for this entire circuit. There we go. Now, what do I have to do for these? Well, C1 and C2, I combine them in this first step, and they're in series. So C12, 1 over C12 is going to equal 1 over C1 plus 1 over C2. So that's that step. Then, so this would be A, call that A. Yeah. For B, what am I going to do? Well, now I have C12 in parallel with C3. So parallel, they're both going to be happily charged, right? So my step B is going to be just C123 is going to equal C12 plus C3. And then my last little bit, I'll call this step C. What am I going to have? Step C, I have them both in series. So this is going to take me right to my equivalent capacitance. So this is going to be C, oops, eraser. 1 over CEQ is going to equal, they're in series, so 1 over C123 plus 1 over C4. Now it's just time to put numbers into that. So I'd need to solve 1, 2, 3 equations. That will get me my numbers. So what is that going to get me? That lets me know how much charge Q total for this whole shebang. So remember, we have our capacitor is the amount of charge divided by the potential. So my CEQ times my V source will give me the amount of charge. So I can rewrite that. That my V source, and sometimes you'll see that is written as like VB for V battery, times CEQ will give me the total charge that this circuit will carry. Now, if we have been careful coming through here, we can remind ourselves that for C1 and C2, Q1 or Q is the same. For C1 and, or the C12 and C13, this one is, the potential is the same. So potential between here and here. Oops, I don't want to do that. That's going to be confusing. My potential is the same. For my equivalent capacitor 1, 2, 3, and 4, my Q is the same. So if I remind myself of that, then once I have my CEQ, the easiest one probably to come back to is to solve for my voltage drop. I know my Q is the same for both, so that will give me the potential drop. I can solve for my potential drop here and my potential drop here. And once I have C123, that means for this little one, my potential drop is going to be the same. So if I solve for my potential here, that means I know what the potential is here, and now I can solve for the charge on each of my capacitors. And then likewise, I work my way up. I've already solved for everything I want to know. What do I want to know? I want to know how much Q and what is the potential drop for each component That is the ultimate name of the game. So first, the equivalent capacitance gets us to how much charge. Then we can take that information along with knowing if something is in series or something is in parallel, what we're going to get. Let's see. I'm trying to decide if putting numbers in here is helpful. And I think I will. I'm going to pause it and write the numbers in to make it clear so you can see. And then we'll go ahead and figure out what the equivalent capacitance is. What I want you to do is to pause this video and solve for it yourself too. All right, so what I did, we'll come back to all my writing I have up there, is I wrote out my little ABC. However you want to keep track of it is you do it your way. That makes sense to you. But remember, we broke down how we're going to come up with the equivalent capacitance for each. So that's the first thing I did, is I figured out the equivalent capacitance of 1, 2. And just to remind you, that was this step here where I combined the two. And then I wanted the equivalent capacitance of combining 1, 2, and 3. So combining 1, 2, and 3, which is going to be this step here. And then the equivalent capacitance of the circuit, which was just combining them all. So that way we could figure out how much charge was on each. And so we get the equivalent capacitance here. That's for the circuit. Then this step, well, that gives me the amount of charge then that system can handle. It's going to be the total amount of charge. And then this other work that you see me doing, this is where people lose themselves. So this is why it's really important that you go through and figure out a way to make notes for yourself. If I wasn't doing this on the screen with a handout right next to it, what I actually would have done is written this or redrew this larger so I could write in neatly each of my values. And then I went through, what do I want to do after I find out my equivalent capacitance? Well, I looked at my next circuit and I asked myself, what's the same? Well, I figured out what the charge was, so the Q is the same. That means I could find the potential drop across each of my capacitors. And then remember, the thing I want is to make sure that my potential drop is relatively close to 0. You're going to be doing rounding on these intermediate steps. And so you're going to end up with things that are kind of far away from your, not kind of, will make you uncomfortable because they're not close enough. If you kept all of your sig figs, you would indeed get the correct answer. So it's just a rounding thing, don't freak out. But what should be true is this potential and this potential should add up to the total potential for the system, so we come to 0. So now I've looked at that and I'm like, okay, I have my potential difference, and that's just using the Q equals, or the CEQ equals Q over V, or the C equals Q over V, because now we've figured out the equivalents. Now we're just breaking them down to each. And so I have my potential drop, and I'm like, okay, C1, 2, 3, what's the same here? Well, I know that from here to here, I'm going to lose this 10.5 volts. So I just wrote that in there, that for the system in parallel, my total potential drop is going to be 10. So that means all I need to do is solve for how much charge each of those are going to experience. Then once I do that, I now have my charge, let's see, the 26 and 63. You can see me down here. That's where I was working on it. There's my 63 and there's my 26. And I'm just being very careful with my notation that I'm keeping track of each. I come back to my drawing and let's see. I got my 10.5, I got my charges. Now, well, I've already solved for everything on 4 and on 3. So the last little step is this C12. And what do we know about that? They're in series, so I know that my charge is going to be the same. So once I have my equivalent capacitors for my C12, now I can use that value, which we've already determined. We determined it here. So I can use this capacitance. And do I know the voltage drop? Yes, I do. Well, no, I know the total voltage drop, but I know what my charge is on each, and I can use that to get to my potential. So that'll give me the potential. Now, my double check here is, remember that this entire circuit was 10.5 volts. So when I determine the potential drop across these two guys in series, they should be darn close to this 10.5. My C3 we already know is at the 10.5. So this whole thing from here to here, each little leg is going to have a drop of 10.5 volts. And there you have it. So this is probably the one thing that gets folks terrified about working on circuits, is that the steps are rather involved. They're not mathematically tricky, but it's really easy to lose yourself on where you've gone and what you have. So what I suggest is, I'm going to post this on Canvas, that you take this circuit and practice breaking it apart and figure out all the components on each. So just do that for yourself and start trying to force yourself to determine what is going to be the most methodical approach that you can take so you don't lose what values you have. Some people like to make a table and like make a note on the side of the table what's equivalent is the charge or the voltage, and like fill in the values as you go. That's handy if you don't want to do it on a drawing, because that seems to get too cluttered for you. It's totally your choice. So the one thing, actually, I mentioned this in our last lecture, was what does doing a dielectric do to change the capacitance? It can increase the capacitance. I'm going to not worry about this for now. This is epsilon naught. So how does it change? It increases the capacitance. And why? You bring something that is going to easily align, so something that's very polarizable. And when the negative charge builds up on the plate, what's going to happen there? I get things that are aligned with the negative charge building up, and bada bing, bada boom, I can get more charge, and there goes the dots. So I'm going to stop there. Next video.